I'm a hydrologist. I work in the area of water resources engineering, and the problem that we have is a very simple one. We have to be able to predict in this region, say the Alps, what is the runoff that's coming from this region. And now, of course, you see that the sources of water can vary, the landscape is heterogeneous, and so actually, sadly, in hydrology, the last 10 years has been the decade of the prediction in the ungauged basin. And the nice thing, when I moved to Switzerland, I ran into Martin Vetterli, and his point was, okay, Mark, that's nice, but let's gauge the basin. Now, Martin, he was profound in that he saw the importance of measurement in environmental systems, but he was actually about 250 years behind, really, perhaps, so this is a quick history lesson in Swiss history. Perhaps the most important Swiss person at this era was, so I'm going to try to say his name, I practiced it yesterday, it will not be said correctly, but Horace Benedict de Saussure. We'll call him Horace from now on. But he was from Geneva, born actually just in France, and then moved at that time, as many people did, to Geneva when he was 6 years old. And he was really, in some sense, the beginning of the mix. He is largely viewed as the inventor of alpinism. He put money and he challenged anybody to go climb the Mont Blanc. It actually took 25 years before it was taken up. And then he was the second. And I like this picture because this is him climbing up. Actually, he had his son with him, similar, and then he had all his, I guess, PhD students, postdocs who are actually doing the work, so that I also feel. But anyway, he was really the second that climbed the Mont Blanc. But what he did is he didn't just climb, but what he did is so if you go to Wikipedia, they have this quote, they measured pressure, they measured radiation, they measured solar radiation, actually all the things. They followed the precipitated water to look at what was going on in the rivers and streams, and so really, in terms of background, it was very similar. And he's so important, of course, that there's this picture in Chamonix, but it's really with the idea of climbing the Mont Blanc, looking toward the Mont Blanc. But actually, why mix? Well, what he did is he actually invented a very useful instrument, and so this is the one thing you should remember from my talk here today, is that he invented the hygrometer using hair. And so we all know what it is to have a bad hair day. So if you have humidity and so forth, maybe your hair will frizz out and so forth and stretch and pull. And so the idea is that you use a human hair, the longer the better, and it will, of course, expand and contract. And so he was able to build this. Actually, here's a picture of his first system that he developed at that time. Now, in the spirit of mix, let's look at this instrument and let's ask, is this a good instrument? So certainly, I took this from the facts about hair hygrometers. So the benefits, no electricity, okay, so that's good. Guillermo Berencheria is always telling me, Mark, we put on the sensor station sensors that don't take a lot of energy. And it's cheap to make. Actually, that's Martin always telling me to build it cheap. And so, a little bit of metal cardboard and, of course, a few strands of hair. That's good. Now, of course, there's some drawbacks. And so maybe somebody like Steve Weiss, who's in the audience, would tell me, sure, the hair can contract and expand, but only a certain amount. And then you have errors at very high or low relative humidity, okay? So, and then the other problem is you're constantly having to go out there and recalibrate these sensors. So there's actually reasons why we would use, say, a capacitance type hygrometer today. But the other aspect that was Horace was interested in was, it turned out it was in the Val-Ferret watershed where he did a lot of his work. I learned this actually just sitting in the Science Foundation last week. Mark Berger, some of you know, in the math department there, said, hey, Val-Ferret, that's where Horace comes from. And so here's a picture of Holly, who's actually in the field today, setting up instruments, and Steve Weiss, and I'll talk about some of his work in a moment in the context of mix. But the Val-Ferret and this history of the hygrometer, among other things, was very important to us. So here are some pictures at various times going into the field. Actually, tower earlier this year that was set up before, looking at the movement of snow, and then here with the team going out to the field. So I'm going to start with, this is Daniel Nadeau, who's now at Laval, and Daniel really went into this catchment. So we're here in this red dot in the southern end of Switzerland, right on the border with Italy, so we're looking north here. You can see, of course, the main Dronsteferre River that we're interested in, and this is a rather typical Swiss watershed. What's slightly not typical about it, I should mention one thing, it doesn't have any major dam or water intake. It does have one drinking water intake. It's about 7 or 8 liters per second that is being removed. But otherwise, it's relatively untouched. Of course, there's agriculture, there are cows and occasionally sheep and so forth that are in the higher parts. Okay, so here's the location where we've been doing a lot of the work, and that I'm hoping in the long term we can continue to work. It ranges at the bottom from about 1,700 and then goes up to around 3,400 meters over here. And so we're going to look at actually just this one slope in this section. So it's ranging just over a 300 meter altitude section. For getting started in this catchment, we started to put up these sensor scope stations that we built with Guillermo. These of course were very useful in terms of starting to learn, both for us, what was going on locally in terms of the hydrology. So we measured the soil moisture, we measured the precipitation. But it was also very interesting, I think, for Guillermo to have and Martin to have the challenges of the communication systems. We learned about the importance of altitude that would happen in the field. And in this particular case, let's come back to our watershed and where I started the talk. What we would like to be able to do is we would like to be able to predict the discharge, so meters cubed per second, in this river at the outlet of this catchment. And then we have the different components that make up the stream. So the total stream is the black, but then you want to be able to predict in hydrology what are the different components so that you can forecast and predict better the stream flow. Now, most of the water actually in this particular catchment ends up infiltrating and then moving as groundwater through it. So that's the subsurface flow in the green. But you'll notice here at the beginning, so this is now the end of June, beginning of July, that we have the contribution due to snowmelt. And it doesn't take much imagination to see that the stream flow obviously is dependent on the air temperature. So the micrometeorology of the catchment plays a major role. Another very interesting thing is if you look through the seasons, we have these sawtooth features. These sawtooth feature will also happen when I talk briefly about the work in Africa that we're doing, but it'll be the reverse. So here in the middle of the day or in the early afternoon, you get a peak when the glacier is starting to melt. So having to understand temperatures higher up where the glaciers are also becomes important if you want to do a good job in terms of the prediction. So of course, we have a section with the snowmelt here. This is our glacier up at the top. By the way, the glacier where Horace actually first went and measured the relative humidity up in that section. And then we have, of course, also these contributions due to the glacier melt, which remember the opposite that will come. But one of the very basic things, and this was also, you could say, inspired by what was done, was if you look at different altitudes, so this was at the beginning, as you can see, we put most of the stations near the catchment outlet, and then only a couple up by the glacier when we first got started. Typically what you do, well, first of all, you're lucky if you have one weather station, and then you use the dry adiabatic lapse rate to say with altitude what might be the local temperature. But of course you can see that locally you can get quite a bit of scatter depending if you're in the shade, depending if you're in a little gully and so forth with altitude. Of course, altitude explains a lot of the temperature, but it was important to be able to have these sensor scope stations to really be able to distribute correctly the temperatures. The other aspect about working in steep alpine environments was the importance of the shadows and the position of the sun during the course. And you see that rather dramatically if we look just at the shortwave radiation coming down on a relatively clear day. Obviously one cloud came in, but you can see how it zooms up, and then at the end of the day, how quickly it will move down. Now, these shadows, both in the morning and at the end of the day, have a very important feature, which is really they drive the mountain wind flows. And so the very simple textbook example is that during the daytime you get the up valley wind, so you have the wind going up, but you also have the slope winds going up the side of the valleys. And then at the nighttime, you have, of course, more drainage flows as things become very stable, atmospheric. And then, so the question that Danielle was interested in was, what happens to the turbulence? What happens to this transition from day to night? Just very, very quickly, in micrometeorology, most of the experiments of the world have been done in places like Illinois, Oklahoma, Iowa, flat. Okay, not a lot has been actually done, relatively speaking, on steep mountain slopes. It just complicates, and I'll just show you a couple of reasons why. So this is coming back in the context of sensor scope. We're starting to put sensors everywhere, but we focused a lot of attention on this one steep slope here, and I'll just show you what were some of the sensors that were put there. So of course we put sensor scope stations up the side, the weather stations. We had an undergraduate who was putting skin temperature sensors, also wireless sensor network. We had one fancy, relatively expensive energy balance station at one point. We probed the boundary there with a tether sonde that went up and down to about 1,000 meters. And then we had one tower that we could put sonic anemometers at up to 10 meters on this side. And then finally, we would look at the skin temperature using a thermal camera on this slope. And the kind of things, of course, that we mentioned earlier, the importance of the radiation budget. What's also very interesting is the importance of the different terms. The black is the net radiation. That's really the driver that's coming down. But what's amazing is the importance of the short wave, so in the solid blue lines that is coming down. If you had a theoretical flat surface, you would have this line right here. And you can see already that the standard calculation that one would use for the radiation is useful, but it's not exactly what is being measured. And then we have, of course, the long wave radiation components, which in this particular case are small compared to the short wave radiation. And then finally, we have the reflected short wave radiation going here. I was just in Florida, and it's interesting, everything is reversed because of humidity. The long wave radiation becomes more important. But what is really stunning and became very important for us, which I had never seen before in all my years of working, was really this drop in the radiation at the end of the day and its relative importance. And it's also interesting, this is just to give you one more little flavor. Look at the altitudes on this slope. So this is on this nice slope, and we have the sensors. So they're spaced over just 100 meters in elevation. And already during the daytime, you see that the temperatures don't line up nicely. In fact, the highest one is the highest temperature, and you would have expected it to be the lowest temperature, but it's not the case. And then, obviously, nighttime comes at the end of the day, the sun goes down, and then the temperatures readjust in different patterns. And these details, how we model the snow melt, how we model the glacier melt, the best way to do it is actually based on the air temperature. And so having the details about the air temperature, and the only way to do it is scatter sensor scope stations across the watershed, will allow you to actually have a look at this. So I'm going to just show you a little bit what's going on to give you just the flavor of one transition that happened on this catchment. So here's the slope. You'll notice a couple of things. First of all, we have grass, we have bushes. You'll see that the features of the bushes will be reflected. They tend to be a little bit cooler, deeper roots, so they're transpiring. You'll see we have 3 sensor scope stations, the red, the blue, and the green. There's another one down here. And the wind speed and the wind direction is given by the vectors there. You'll see there's also a yellow station that was closer to the river. And then finally in this rectangle, you have the skin temperature as measured using this thermal imager. So this scale will change. So at the moment, this is relatively warm. It's in the daytime, 28 degrees down to 18 degrees. Okay. So I'll just, we can run it twice, but in the interest of time. So I want you to look at the temperature evolution and also the wind speed. Notice that the winds at the moment are pointing uphill. So this is the upslope flows. And then over time, we'll have the shadow appear and things will change. Lower winds have died. The upper one doesn't feel it yet, but already down below, the winds have started to change direction, and now finally the top wind has died. And you'll notice that it's become more uniform in terms of the temperature, relatively cool. Okay. Now, of course, we can look at this, but we wanted to do, you know, quantify what does this really mean for us. So I just show, first of all, we show the axes. So the slope x is in the direction of the prevailing wind. Z is in the vertical perpendicular to the slope. And this is, I'll just show some of the things that have been able to be measured thanks to SensorScope for the first time. So the first is, for those of us in micrometeorology, I'll just give you one example. This is the flux of heat, the sensible heat, with elevation. And we normally assume that we have a constant flux. That means if you take the derivative, of course, if you have a constant flux with elevation, it should be zero, right? But you'll see that during the daytime, it's anything but zero, the green line. And so this is a very this raises lots of important things. We used to just measure at one height and make the assumption that since it was constant flux, it would be the same as what was coming out of the ground. But obviously on a steep mountain slope, that's not going to work. Maybe at nighttime, this could be the case. And the other term that we were able to measure, because the winds nicely lined up with our sensor scopes, we could measure this term, the velocity of the air times the gradient of the temperature with distance. And for the first time, we could have an idea about this term and the advection term in this case. Again, the importance of being able to have these spatial measurements really opened up for us some of the importances, some of the assumptions that we had made previously. For example, when I was working at UC Davis, in flat agricultural regions, just would not hold in these mountain environments. Another aspect is just the turbulence itself, the turbulent kinetic energy. You have the change in kinetic energy with time. There's a source of buoyancy, there's a source of mechanical shear, and then ultimately, at the molecular scale, we dissipate the energy, fortunately. If you look at, again, the budget during the course of the day, in the daytime, we have a lot of buoyant production. The shear production before the time of sunset actually drops off much quicker. And then at nighttime, everything reverses, of course. In the daytime, it's a production. At nighttime, the cold air tends to descend, and so it's actually killing the turbulence. And then the shear, the flow of the wind down the slope, actually is producing turbulence. What's very interesting is we have this very nice calm period that we could identify systematically every day at the end of the day, and this also becomes very important in terms of how one would formulate models using the SensorScope station. So these were some points that this also gave us. We started to develop some simple models about how the winds might look, and we were fortunate to be able to deploy some wind lidars. This was with Mark Parlange and Marcus Holtmark. Two more people to add, Carl, to your picture, of people leaving to the US, I guess. But these are the winds going up. Actually, I really should start this again. But you'll notice that if it's yellow or red, it means the wind is blowing away from you. And if it's blue, it's flowing down towards you. So the red here is the hill, and then what Mark did is he just scanned the laser like this, and so he was able to look at the wind. So we're going to do this again, but what I want to do is, what I'd like you to notice is that it's not that simple according to the patterns. So, you know, during the daytime, yes, the winds are going up. Obviously, periods are changing. Now we're in the nighttime, 11 o'clock, midnight. Down near the ground, you'll notice that it is actually could be flowing down along the slope, whereas you would have sections higher up that would actually be flowing up the slope. So that complicates the life that one would have to measure. When I started, I wanted to talk about the importance of predicting the stream flow. The other aspect that became important in the context of the mix was we actually took our catchment and we started to break it up into sub-catchments with Raphael Munzner to look at really the, if you will, the veins of the catchment and the stream network that was going out there. And so that raises the question, how do you measure the stream flow in a catchment? And this is the project that was started with Sabine and Pascal Foy. So you have, so hydrology 101. So what you might be interested in is the height of the water in the stream and the discharge, okay, in meters cubed per second. Okay, and this is known in hydrology and water resources as the rating curve. Now typically, if you have lots of money, you can go in and you can line the bottom of the stream with concrete in a section, and so that the bottom of the river doesn't change. And you can see over the years, so 2009, we would go out and measure the discharge using this salt dilution method, and then we would plot the curve, and it would look beautiful for that year, and then we went the next year, and we would, in 2010 in green, and we got a different curve, and then 2011, we got yet another curve. And of course, what's happening in the Alps is that we have the rocks that are moving, the erosion, and so forth. And so we'll have shifts in these curves due to the sediment transport in the river. And quite a bit of scatter in terms of relating height of the water, which is very easy to measure, just to measure the pressure. And you can put that on a sensor scope station, which we do. And the idea is we could do this in different sections of the catchment. But there was a lot of uncertainty, really, in these measurements. And actually, so one of the nice discoveries that Steve Weiss made was that we were also measuring the electrical conductivity in the stream, not just the height of the water. And if you plot the conductivity versus the negative log of the discharge, so you have in the black is actually the conductivity, and then this has been scaled so they fall on top of each other. But you can notice that actually the conductivity is actually a very good predictor of the discharge. It's not just the height of the water in the river that's important, but the conductivity. And the reason for that is if the water is really that base flow that I mentioned at the beginning, it's going to take all the salts out, and you're going to have in the rocks, and you're going to have a higher concentration. If it's really the snow that's just melting and running off the surface, obviously it has less of the salt, you know, the ions that would be going. And so this is an additional piece of information. It's not just the height, but you can use the electrical conductivity, and ultimately you can develop a better water measurement device. And I'm happy to say this paper got accepted this morning with one of the reviewers writing, please can I use this method with my students before the paper comes out? So it's like, of course. But the point is, if you just use the water height, you get an uncertainty spread, say for a given discharge in the blue. If you just use the electrical conductivity, you get an uncertainty spread with the black. And if you combine these two information, then you can squeeze a little bit the uncertainty with for a given discharge. In the interest of time, I will stop here about Valferré, but it's in the process of looking at the micrometeorology, having these data, we're constantly actually realizing we need to measure in new places. We have spots where we put sensor scope plate and discharge measurements elsewhere. We've also been able to link this very much to the beginning of where are the sources of the rivers, so we can predict actually very nicely where are the sources, and then with good mountaineering students, we've gone to the different locations. This is very important in the context of looking at predicting landslides, so mountain risks, and it's opened up, in a sense, a whole new line of research. as Carl mentioned, we wanted to also go to warmer climates, and the Savanna region of Africa, we all hear about the Amazon, but it's because of the cutting of the forest and the importance of the global circulation. But the Savanna of Africa is also extremely important, and is also under a lot of pressure in this region due to the movement of agriculture in this region. And so with Natalie separately, who's measuring this particular tree, and Theo Mande, who's preparing the sensorscope stations there with Guillermo Barancheria, we went to the southeast part of Burkina Faso, really with the idea of trying to start to understand the hydrology of this region and what would be the impacts of agriculture on the hydrology and the erosion. So, you know, I complain about the number of sensors we have in Switzerland. It's dramatic in Africa. We went to visit the National Center weather station, and it was largely abandoned. They still were keeping it clean and cutting the grass, but none of the sensors were working. So it's very, very tough, you know, in these parts of the world where largely we now rely on satellite information. It's important to have the ground truth. So Theo built on this ephemeral stream. He put in a stream gauging. Natalie, in this picture, is starting to monitor the water table, the aquifer in this region. Of course, we started very basic again in a watershed, putting out sensorscope stations, looking at the distribution of the precipitation, trying to understand how variable it would be. And one of the interesting things, so I talked about the glacier melt, and now we're going to, oops, this doesn't come out so well, but let me try to tell you what we're seeing here. So in the top is 4 curves that Theo and Natalie measured using the sensorscope stations of the diurnal evaporation, and underneath it we have the stream flow that they were measuring. And so of course it doesn't take much imagination to see that instead of having the peak with the glacier, we have now a dip during the daytime when the plants were, or the trees were extracting water and evaporating it into the atmosphere. So I hope this picture, yeah, this one shows up much nicer. So these were, for example, those 4 days. You can see the evaporation. And then those 4 days for the discharge. And so what Theo did is he said, okay, we start at the beginning of the day, the end of the day, and then we're going to look at this dip, and we're going to look at the corresponding evaporation. And you can do a very simple back of the envelope. You can say, well, how much evaporation was taken place, what was the discharge, so, and from a certain depth, and then what was the loss, if you will, this drop in the discharge. And then you can solve for actually the contributing area that's controlling the stream flow in this watershed. And so you divide one by the other, and then on average for a given day, you can say how many meters squared, how many, you know, say 1 or 2 kilometers squared were contributing. And actually it's very interesting because you would think, it turns out it's actually really this region right by this particular stream in Africa that becomes very important. It's really the riparian vegetation that controls what's going on. So when you start to think about how are we going to model the water resources of this region, you have to realize it's not just the whole catchment that's playing a role here, but it's really that section that is along the stream that becomes extremely important. Okay. I'm going to stop here. I want to say that if the 2 things, if you know, at the end of a project like this, to ask, I think the close collaboration of environmental engineering and computer science and electrical engineering certainly allows us, and I hope I gave you the flavor of some new environmental phenomena, whether it's the mountain slopes or whether it's the airflow in the mountains and so forth that we can understand, or whether it's the stream flow in the savanna that's important. And I think also what was very nice was this, actually trying to go to the field, trying to deal with the problems that one faces when one goes to these environments. You know, how to make a rugged weather station that can withstand the Alps, the cold, the wind, the rain, the snow, or in the case of Burkina Faso, the others. You know, again, questions about how do we deal with communication systems in these environments. It's not trivial. And then the final thing, of course, is that there's great similarities between the Swiss Alps and in Africa. And I have this last picture I'll finish with, which was we, of course, dealt very closely with the people that were herding the cows in the Alps and where we could put our sensors, where we could not put our sensors. It's an ongoing discussion all the time. I think we enjoy discussing about it. But this was also a discussion, and this is Natalie talking with 200 cow herders that had come through, and that you can't design a sensor scope station for, as the cows come marching through your fields and knock over your sensors. But I was very impressed. And actually, after this meeting, Natalie, on her own, got everything working beautifully again, and so we've never had any problems. Actually, I should mention, in all these years, the 100 stations on campus, or all the stations out in the Alps, or for that matter, all the stations in Africa, we've never had any theft, and we've been able to, in both cases, I think, to interact closely with the local communities, and that's been also an essential part, I think, an important lesson learned in this work. Okay, thank you.